around these carbides because the carbides basically suck up all the chromium. And so you've got these regions that are really not stainless anymore because they've got a bunch of little chromium carbides in there, but they don't have the general chromium in the matrix that's needed to be corrosion resistant. And so then when the material is exposed to atmosphere, you end up with all these regions along the grain boundaries that can be corroded. The way to prevent that, like I mentioned earlier, is to use, there's a couple of ways to do it. One is to control temperatures. Another is to use the low carbon alloys. If there's not as much carbon there, there's not as much ability to form the carbides. The other one is to stabilize it by using titanium or niobium in those alloys 321 and 347. What happens there is the carbides actually form preferentially with the titanium and the niobium instead of the chromium, and so the chromium is left behind, and you end up with titanium and niobium carbides at your grain boundaries, and that doesn't lead to that that zone that is susceptible to corrosion.
When you're saying interpass temperature, that's interpass, and the temperature between that and taking another pass, you're saying you want to try to keep it cool?
Yeah. You don't want to. You want to keep it below 350, basically. So the way you do that is, maybe you make a pass. Maybe you have to wait a little while. If you just keep welding right on top of one another, you're going to get your temperatures up too high, and you're going to be more susceptible to corrosion. A couple of other things that are worth mentioning. There's something called rapid solidification effects. And when this occurs is actually when you're doing a welding process where solidification happens really fast. And that's typically a high energy density process such as laser welding or electron beam welding or even cladding. Because of the physics of those processes, the solidification of the material is much quicker than if you're doing a typical arc weld or something like that. And when that happens, there's actually a shift in those solidification modes. And so it's important to remember that if you're laser welding or electron beam welding on austenitic stainless steels, and I'll show you some diagrams that demonstrate that. This is something called a Sutila diagram. What Sutila did is he figured out that, once again, here's these chromium and nickel equivalents. He figured out that at about 1.5, and this goes back to that other diagram that I showed you of cracking susceptibility as well. This is with standard welding processes, that anything above 1.5 you didn't get cracking, whereas below 1.5 you typically got cracking. But when people started using laser and electron beams to weld, they noticed that the Sutila diagram didn't always work, and so more research was done. Something called a modified Sutila diagram was developed, and you can see that the solidification mode actually shifts to where you need to be over to about somewhere around 1.7, somewhere between 1.5 and 1.6 to get to no cracking versus cracking. And so in the welding of stainless steels, people have developed a lot of these types of diagrams to help you depending on what you're trying to do. So it's just the main thing here to remember is that if you're welding with a high energy density process, you're going to need to be more worried about cracking than you were otherwise. So I spent the majority of the time on austenitic stainless steels I want to spend a little bit of time talking about both ferritic and martensitic stainless steels. Next we'll go to the ferritic stainless steel alloys. Ferritics are really, they're probably the most simple alloys. They're based on generally just on the iron chromium system. So they're iron with enough chromium in them to be not corrosive. They also have a pretty big range of typical compositions, depending on what the alloy is going to be used for. The more alloying element you put in it, the more expensive it is. So you end up with a wide variety of compositions in all of these alloys. Like I said earlier, the chromium content in ferritic stainless steels is typically more than 10. It gets you to avoid the gamma loop and puts you over in this region where you're going to be solidifying from the liquid into an alpha or ferritic chromium microstructure. There's two types of ferrite. There's delta ferrite and alpha ferrite. Delta ferrite is typically a higher temperature ferrite, and alpha ferrite is a lower temperature ferrite. I'm not going to spend a lot of time on this other than just to show you that there are kind of different levels of chromium leading to different groups of ferritic stainless steels. The first ones to be developed were these medium chromium stainless steels. 430 is one that you would probably hear of a lot if you hear of ferritic stainless steels. That's kind of the workhorse ferritic stainless steel alloy. Later on, as people were trying to improve things like weldability, the more carbon you have in something, generally the harder it is to weld. And so they started trying to lower the carbon and the chromium levels a little bit. These are actually the most economical. Like I said, they have less chromium in them and less of other alloying elements. And then in more recent past, people have started developing higher chromium alloys, and these are typically proprietary applications. There's something called E-Bright. They're higher in purity because of the higher alloying elements. You've got to be more careful about the purity. They're also, because of the higher chromium content, the highest in resisting corrosion. They're also the most expensive. Some of the things that the ferritic alloys are typically used for, it really does depend on the chromium content, but automotive exhaust systems use a lot of ferritic stainless steel. The trim on cars, where you do have chloride containing environments and you can't use austenitic stainless steels, the ferritic alloys are a great substitution there. Some of the limitations that you need to remember are the service temperatures, and that's because you end up forming some brittle phases in the material when you get up above 750 degrees F. Also, just because of the nature of the alloys, toughness and ductility is not quite as good as it is with the austenitic alloys. And then on the lower chromium alloys, you do have to worry about corrosion resistance. That's why an automotive muffler that's made out of 409, for example, it's still going to rust eventually, but it's more corrosion resistant than a plain carbon steel. Sure. Okay. Some things to consider when you're welding the ferritic alloys. Preheat is really dependent on the alloy type. Preheating is intended to slow cooling rates and reduce shrinkage stresses and the amount of martensite that might form in many of the ferritic alloys because of the way they fall on those diagram, the Schaeffler diagram and other diagrams that I showed you. You do end up with a little bit of martensite in the structure. Post-weld heat treatment can also be used. Sometimes you use that as a way to temper the martensite, which is a very hard structure, hard phase. Sometimes you've formed carbides or nitrides that are not desirable, and so you might want to try to dissolve them. And it can also reduce residual stresses. The filler metals that are typically used, a lot of times you use a matching filler metal. Sometimes, depending on the application, you would actually use an austenitic filler metal. And nickel-based high nickel alloys can also be used. Depending on the application, if you're basically, if you're trying to improve ductility and toughness and things like that, is when you would use the austenitic or the nickel-based alloys. There's basically a couple of things that you need to worry about in welding the ferritic alloys. One is cracking. The other is there's various forms of embrittlement. Cracking due to weld solidification and liquation cracking, it's not as high in the ferritic alloys as it is in the austenitic alloys. It's not as big of a concern. But hydrogen-induced cracking can become a problem if you've got high hydrogen levels in the environment. And the intergranular stress corrosion cracking and grain boundary sensitization can also occur in ferritic alloys. Like I said, there's a few different types of embrittlement that can occur, and that's due to a couple of different types of things. It can be due to excessive grain growth in the fusion zone or the heat affected zone. Because you don't have a lot of second phase in a lot of these alloys, as you heat them, the grains can typically grow to a size that can lead to embrittlement. You can also get precipitation of carbides and other phases that can lead to embrittlement. And embrittlement always reduces toughness and ductility. So along the lines of embrittlement, there's something called sigma phase. I don't know if you noticed when I had the iron chromium phase diagram up there. I'll put it back up for just a second. This right here is sigma phase, and it can form in these alloys due to precipitation and due to temperature ranges that are deleterious. And as that happens, you can lose, like I said, you can lose your toughness and your ductility. There's also something called 885 degree embrittlement, which is the formation of an alpha prime phase. and it's most rapid at 885 degrees F. That's why it's called that. And so the main limitation of the ferritic alloys is the temperatures that they can be used at. Along the lines of what we talked about with the austenitic alloys and the carbide precipitation, you need to watch that a little bit with the ferritic alloys too. Along the grain boundaries, you can lose some corrosion resistance. The same type of sensitization where you form the chromium-rich carbides that lead to that. It's actually called a denuded zone, I believe, where there's not enough chromium there to keep it corrosive resistant. So those are the issues with the ferritic stainless steels. We're basically out of time for today. I think what I'm going to do, I'm scheduled to talk to you again about the nickel-based alloys and their weldability, and I don't think that will take quite as long as the stainless did. And so what we'll do is we'll start with the martensitic stainless steels, and we'll go through that for a few minutes, and then we'll spend the rest of the time talking about the nickel-based alloys. So I think you all have my email address, my contact information on the sheets that were handed out on the first day. If you have any questions, I know that was a lot to digest in one lecture. A lot of that stuff was taught to me originally in about a half a semester. So I tried to go through it quickly. I know it's a lot to try and understand. So if you have any questions, any things you're interested in, I'd be happy to talk to you more or give you some resources or something like that. Thanks a lot.